Hi everyone, welcome to this new lecture of fluid mechanics. In this lecture we will discuss the derivation of metacentric height. In the previous lecture already we have discussed the concept of buoyancy and center of buoyancy and metacentric height. So in this lecture we are going to derive the derivation for metacentric height. So for this I have taken a body which is floating on the water, and this is the water surface is there, and this is the body which is present, and this is the front view of this object, and this is the top view of that object. Okay, now this body is situated, or the body is actually how it is means it is like this. So this is the width of this, you can say, and this is the height of this body, and this is the length of this object. So this is L and this is W, and this one we can say the height of this object. Okay, so this is the body which is floating on the water. So when it is floating on the water, okay, we can see, suppose this is the arrow mark is there, and which is front view of this object. So when it is floating on the water, we can see this is the front view of that object, and this is the top view of that object, what we can see from there. Okay, it is not properly coming. Yeah, so now if you draw the axis line of this object, if I draw the axis line of this object, I can draw it in this one. This is the axis line of this object will be there for this, and for here if you take along the top view, this is the axis line of this object. Okay, now the center of gravity of this object will be, we know that this is the center point of this body where the total object will be total weight of this object will be placed. Or you can say if I show the center of gravity in the front view side, then I can put it here, or else we will become in the middle point of this object where it is the total weight of the body is existing. So that's why the center of gravity of this body we have kept in the middle of this object, that is G point, and let me tell you, the G point will be defined the center of gravity point, and the center of buoyancy, that is nothing but how much the body is inside or immersed inside the water. Based on that we can find out the center of buoyancy point. So that is also like at which point the body, the total force of this body is acting on that point. So that is B point, center of buoyancy point. Okay, and now this is the normal condition is there. Now suppose if you want to rotate this object with slightly with an angle of theta in a clockwise directions, okay, then only you are going to able to find out the metacenter and metacentric height. Okay, so this object which is there, let me draw this. This is the object which is there present, and this is the axis line of that, and this is the B point, sorry, G point of this, and here B point is there. Okay, now when it's going to rotate in a clockwise direction, then we can see after rotation the object is placed like this. Okay, so after rotation you can see this AB point which is initially here, okay, it is going to change its location. So the A point was changed from this point to the displaced point A point here, and B point came down below the surface level of this, and it came here. Okay, and the new point what was there, that is A dash and B dash, it was given. Okay, so it is in this location it was there. Now it is changed to this side, and this B point is changed to again one more location of this. So you can see this is the midpoint of this, we can give it O, and this one B dash and B after rotation, and this is A, and before rotation this one A dash. Okay, now if I rotate this one, then we know that the force of buoyancy which is acting at this B point, which is acting initially at this B point, now this is going to displace in the right side, in this, like which side it is rotating, based on that it will be moved. If it is rotating in this side, left side, then B point will be rotated in this side, it will be moved to this side. Okay, so now it is rotated in the clockwise direction. That's why the B point, the force of buoyancy point was changed from B to B1 point. Okay, now the force of buoyancy will be acted on this, because you see, after rotation, if you see, the area of this right side of this body is increased. This much area was there. Initially it was like a square type is there. Now if you see, now it is not a square, some area was increased on this right side. Similarly in the left side the area is decreased. Okay, now that's why the force of buoyancy is changed from this B point to B1 point, but here G point will be as usual, there will be no changes on that. Now the force of buoyancy, this point line of action, if you extend this line with an vertical upward, that is going to meet the axis line of the body. Okay, so that meeting point is called metacenter or aim point. These things already we have discussed previously in the previous lecture. And the distance from this aim point to the center of gravity point is known as metacentric height, that is denoted by GM. I hope you understand. So now we'll go for the derivation for this. Now see, due to this rotation, okay, what are changes happened in this? Now initially it was, the force of buoyancy acted at this point. Now due to these changes, okay, the force of buoyancy also changed. Okay, in the right side also and left side also, both side the force of buoyancy is changed. Now after this rotation, if you see, okay, this is the structure of diagram it formed. Okay, and this angle of this line of action and the axis line is theta. So one more notation, that is theta. Okay, so now to derive this metacentric height of this body, okay, so let me consider a small strip of this object. Okay, the small strip in the sense, this is the, suppose one side is there, that is nothing but, this is nothing but O point, and this is B dash point, and this is B point. So let me consider a small strip of this object, okay, which is at a distance of x from here to here, it is x, and the thickness of the strip is dx. Okay, now if the strip I want to show on this object, then I can show here, this is the strip is there what I have taken on this object, and this is the thickness of this is dx, and the distance from this center point or from the axis line to this one, this distance is x. Okay, that only I have shown here, x, the distance from here to axis line to here, and this is the thickness of this, that is dx, and length of the object is L. Okay, let me consider a small width of the small strip on this object, that is dx, and the distance from this center point is x. So in this strip also there is a force of buoyancy which is acting on this, that is vertically upward, so that is mentioned. So this force of buoyancy which is acting on this strip, you can mark as dFv, and the force of buoyancy which is acting at the left hand side, that is vertically downward, you see, and this force of buoyancy at the right side and left side both should be equal. Okay, then it is going to be balanced one. Okay, now so for this let us start the derivation. So the derivation will be started, first we'll find out this strip what we have taken here, the strip height. Okay, because this is the length of this object what we are from the center point, and let's find out first the strip height. So this one, yeah, the strip height h equal to, we can write what is the length from the center point. So initially it was this one length, and the height was nothing but there. Now after rotation, after these changes happened, okay, some increased. So how much is it increased? Now x into how much angle of rotation, this angle is actually theta. Okay, so the angle of this one we can write, that is BO and B dash. Okay, BO B dash. So BO B dash is nothing but we can write x into theta. So these things also we can write in such a way also. Suppose this is the object is there, if you want to mention in terms of sin theta, then in sin theta you can write here, and h equal to what? H is the height, means from here to here, that means the height of this strip how much. So that one you can write h and divide by this hypotenuse is there, opponent hypotenuse, we can write h by x. So we can write h equal to x into sine theta, and in the sine theta we can write x into theta, that is when the theta is very small, so we can write sine theta equal to theta. So that also we can write in this way. So h we got it. Now what we'll do, we'll find out the area of the strip. So area of the strip is nothing but, we know that height into thickness. So height into thickness of the object, that is thickness. So that one we can write h value x into theta, and thickness is thickness of the strip is dx. So x into theta into dx. This is the area. Now what we'll do, we know that the length of this object is L, so we'll go for calculation the volume of this object. So volume we can write, we know that area into the length of this object. So area already we got x theta dx, and length is the L of this. Now this is the volume of this object. So next we are only calculating for this, all these things for the strip only. Okay, this everything is calculating for the strip. Now next we will calculate the weight of the strip. So weight of the strip we can write weight of the strip equal to, we know the W equal to mg. So in the place of m we can write rho into v, because we know that density equal to mass by volume. So mass equal to density into volume. So that I have written here. So now we can write rho into g, and volume what we got, now x theta and dx L. So this is the weight of the strip. Now the strip what I have taken, this is for the right side of this axis line, correct. Now same thing, if I take a small strip of a thickness of dx at a distance of x towards the left side of this. Left side means, if you see, this is the axis line. So the strip what I have taken here, that is in the right side of this. Now similar things if I consider the left side of this, okay. So left side of this means any one of this object, okay. So how much distance? That also distance of, so what it mean to say, the strip what I have taken here, that is from here to here a distance of x. Again similar thing, if I will consider a small strip at the left side of this, so what will be the distance? That also will be x, and the width of this will be dx, okay. So if you see the force which is acting at this point, like both are opposite in directions, okay. So these two forces, if you see, both are acting opposite direction, so that actually constitute a couple formation will be there. So one force is here, another force is there, and the distance between them, okay, how much is there. So this couple formation we can write, that is the moment of, we can write the moment of couple, okay, equal to, we can write what is the force acting on this point, or what is the weight of this object here, and what is the distance traveled from this point between these two strips. So we can write the weight of this each strip into the distance between the two strips. Distance between two strips, here one strip, here one strip, suppose. So distance will be x plus x, that is 2x. So we can write weight of the object what we got here. So that is nothing but rho g x theta L dx into 2x. So this is the value what we are going to get in this. Now if we multiply this one, so what will get? 2 rho g x square theta L dx, okay. So this is the moment of couple we got on this, okay. Now this is only for strip we got. Now if you want to calculate the moment of couple on the whole ways, on the whole object, the object is actually waste surface what we have taken, that's why whole waste, okay, that is the body, so don't confuse on this. Whole body if you consider, then what we need to do, just we need to integrate this object what we got here. So that is equal to integration of 2 rho g x square theta L dx, okay. So this one we can give a equation 1. Okay, now the next point what we will do, yeah, I'll go to the next slide. So yeah, so here so let me find out the next one, the moment of couple, okay, due to the shifting of, you know, the force of buoyancy. The force of buoyancy shifted from where, and the force of buoyancy shifted from or center of buoyancy, you can say the center of buoyancy from B to B1. If you see this, now see here the center of buoyancy was B point. Due to this rotation, okay, this is the changes. So the center of buoyancy changed to from B to B1. So now let's find out the moment of couple. The moment of couple, okay, due to the shifting of center of buoyancy from B to B1. So this one we can write, that is nothing but the force acting on this, the force of buoyancy into the distance. Distance is nothing but we can write B1. Okay, now this B1, what we can write again similarly, B1, if you see that one we can write theta into BM, theta into BM. If you see the structure, that one how it is, let me draw it here. Yeah, so this is the M point, and this is the B point, and this is the B1 point. Now this is the angle between this theta, correct? So now B1, if you want to identify, so I can write in this way. So I can write also sin theta equal to this opponent by the hypotenuse. Okay, so that one I can write in this way also. Okay, now in this force of buoyancy which is there, that also we can write FB, we can write also weight of the object. So now this equation I can write W into, in the place of BB1 we can write BM into theta. Okay, now W value already we got previously, so that is nothing but okay, W for this we didn't get anything, so we'll do one thing, let's keep equation 2. Now this moment of couple and the moment of couple what we got previously here, the moment of couple, this one, let compare these two. Okay, because these two equations will be, you know, these two couples will be same. So let equate this equation 1 and 2. So what will get, equation 1 and equation 2, equate this, will get W BM theta equal to integration of 2 rho g, okay, x square theta L dx. I hope this one. Okay, now again let me write this. So W BM theta, let take some constant term outside of this, so that is 2 rho g theta integration x square L dx. So let theta will be cancelled. Okay, now this L dx part, if you see, L dx is nothing but L dx we can write, that is the elemental area on the water line. So elemental area on the water line, so that one we can write dA. Okay, length into the thickness of that or width of that. So now again we can write W BM equal to rho g to integration x square dA. Okay, now this 2 into integration of x square dA. Okay, this one if you see, 2 integration x square dA, this actually, this is the second moment of inertia, this is the second moment of inertia, okay, of that top view, okay, of the body of the water with respect to y axis. This one, if I take this is the top view of that object and this is the y axis, along that what is the moment of inertia will be there? Now 2 into x square into dA. Okay. Yeah. One moment of inertia, that is x square dA will be integration of x square dA, and this is 2x square dA is there. So what I can write in place of this? So moment of inertia, that can be marked I. Okay. So here what I'll do, integrate implies Bm, keep Bm one side, this equal to rho g, and this is I, rho g I divided by W, correct? Rho g, this part, total part is going to convert into moment of inertia, and this W I have taken to this side, W. So W, we know that again, previously I told that W equal to mg, and in the place of m we can write rho into v into g, rho into v into g. So we can write rho g I divided by rho g v. So rho g cancel, I by v. Now Bm, what we got there, if you see the diagram, let me draw the diagram again here. So we have seen this is the M point, correct? And this is the G point, and this is the B point. Now Bm, from here to here, what we can write that one Bm? So Bm we can write Bg plus Gm equal to I by V. Now we need to find out the metacentric height equation. So what I'll do, I'll keep Gm one side and I'll take that Bg to other side. So that is nothing but I by V minus Bg. So this is our final derivation or final equation for the metacentric height. Okay, so I hope you clear about this. So how to find out the metacentric height derivations. If you are having any kind of query regarding this or doubt regarding this, you can give a comment on the comment box. Thank you all.